So far, we have seen a case where two data points were known, and through linear interpolation, we were able to draw a line between these two data points, and all the intermediate points were lying on this line. Hence, once we knew the slope of the line, we were able to calculate all the missing intermediate data points. Now, what happens if the underlying data is not linear? What happens if it's a non-linear data? Then how do we go about implementing linear interpolation, and what are the implications? So in this section, we are going to investigate this problem. So first, we are going to simulate a non-linear function. In our case, it will be minus x square. So horizontal axis is x-axis and vertical is y. And as you can see that this is a non-linear function, a quadratic function. We will then sample this function so that all the missing, so that we can simulate missing data. So these red dots, 10 red dots are the sampled version of this particular non-linear function. And then we are going to calculate intermediate missing points using linear interpolation. So in this graph, you are seeing that the red dots are known to us. This is the known data. And we are trying to investigate green points, which are intermediate data, and trying to fit linear interpolation in this. So what we'll see is that we will be able to draw lines connecting these green dots. But since a line cannot curve, that's the reason we are going to face errors while using this linear interpolation algorithm. And if I zoom in into this part, you will clearly see that there are errors if we use a linear interpolation on a nonlinear data. So over to Python. So let's start by generating a nonlinear function. Let me create the x-axis for it. So I'm going to use numpy's linspace function for this. So the x-axis will start from -2, it will go to 2.5, and it will have 100 linearly spaced numbers. And to calculate y, I make a nonlinear function x minus x square, and this is a function that we are going to sample then later on. So let me just plot this function, and activate my general plot settings. Okay, so there's this error. It has to be plt dot. So there we are. This is the nonlinear function that we are generating. Now I'm going to sample this function to have discrete points on this curve. That can be done by sampling this curve. So how I'm going to do is this, let me make another array, and I'm going to take X array, and I will skip 10 samples and then read the 11th sample iteratively. So let's see what this X values looks like. I'm going to disable this plot function. So this, just a minute. So I need to print this, and I will also disable my plot settings here. So there you are. Here I have taken 10 values of X, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the 10 sampled values of X, and I am going to, similarly, I'm going to sample the y-axis. And I'll just copy this code, and so there we are. This is these are all X values, sampled X values, and these are corresponding Y values. Let me just plot them and show it to you how they look. Let me just disable this. Let me just activate this print, and I'm going to plot these sampled values and again activate my plot general settings. So here we are. So now you see that these are 10 points that have been sampled from y is equal to minus x square function. And the idea is that we will specify intermediate points, the missing data between these two sampled points, and so on and so forth, and then try to recover those points, try to calculate the y values of those points using linear interpolation. So if actually you, just to prove it to you that all these points are on the original function, minus x square. We have just taken 10 samples out of this whole function. Okay, so let me just disable this. Let me disable the plot. And so what I'm going to do now is I'm going to initialize 2 arrays to save my intermediate x and y values. So I will call them x intermediate. It's going to be a empty list, a placeholder, and correspondingly for its y value, I'm going to initialize a array. So how I'm going to calculate these intermediate values is like this. Let me just show you how this works. So let's say I take linspace function, and I, from this array, x values, the sample data basically, x values and y values, I'm going to take the first element and the next element, and I will have 3 points between these two. This is the start, this is the end, and I need 3 points here. So let's see what is the output. So if you remember, this was the sample data on x-axis, and my attempt is to generate an intermediate point which is between this -2 and -1.5, and then in the next cycle between -1.55 to -1.09, and so on and so forth. So for the first iteration, I have gotten -2, which is coming from here, and I have also got -1.5, which is here, and the intermediate point is here, -1.77. So I just need this intermediate point. So what I will do is, I'm going to just take the second element of this list, and here I have extracted that intermediate point. So I'm going to use this logic in a for loop so that I calculate, I get an intermediate point between these two, then in the next iteration between these two, and then in the next iteration between these two, and so on and so forth. So I will not be needing this. This was just to show it to you. So I'm going to disable it. So I'm going to initialize a for loop, which is going to iterate in the entire sampled space of x-axis. This is the sampled space of x-axis. So for I in range, which is the length of x values -1, and what do I want to do? So I want to calculate my intermediate x, and I just now showed it to you that this is the logic that works. I just need to modify this logic to get it iterating. So 0 will become I, and this will become I plus 1, and let me call it x point. Okay, so I'll be able to get, in the first iteration, I'll be able to get between x, first element of x and the next element of x values. So slope will continue to remain the same as we calculated previously. Slope is going to be, now with each y value, I plus 1, I'm going to subtract it from the next y value, the previous one. So what I'm doing here is basically, these are the y values, so I'm taking this point and subtracting it with the first one. So this is what this line of code implements, and I'm going to take x values, and again the same logic, I plus 1 minus x values I. So what I've done is, to calculate slope, I have subtracted minus 2.39. I have taken minus 2.39 and subtracted minus 4 from it. That becomes my numerator. And then I've taken minus 1.55 and subtracted it from minus 2. That becomes my denominator. Numerator by denominator is the slope for these 2 points. And then I'm going to repeat this entire exercise for the complete array. So that's how the slope is calculated. So I'm going to now calculate. I have found out the intermediate x point, which was this. So I'm going to calculate the corresponding y point for this, which is coming from linear interpolation, slope into my x point minus x values. So this is coming straight from linear interpolation, and this should be this bracket, and this is the first y element. So this is nothing but this is what is linear interpolation between 2 points. Okay. Now I'm going to save x point and y point in the arrays that I've initialized earlier for these intermediate values. So I'm going to say x intermediate dot append, and then I'm going to save this x point there, and I'm going to do similar thing, y intermediate dot append, and I'm going to save the y value. So in the first iteration, I will calculate one intermediate value, which is going to be between this and this for the x scale. And then I'm going to calculate the slope. And the slope is nothing but this minus this divided by this minus this. And I'm going to loop through the entire list in the for loop for slope at every point. And then I'm going to use this formula of linear interpolation to calculate the y point. And then I'm going to save both x point and y point in the arrays that I've in the list that I've initialized here, and save all the points there. For the ease of further plotting, I'm going to convert these lists into arrays. So I'll just use, and I'll just copy this code and place it here. This becomes y, this becomes y. And let me just print them so that you can, yeah. So as you can see that I have calculated all these x intermediate points and corresponding y intermediate results using linear interpolation. So let me just plot them and see how they look. So there you are. You can see that these are all linear lines that are connecting these intermediate points. Actually, what I can do is I can disable this plot and I will show it to you here. So here we are. You can actually see, so our red points are known points, sampled points of minus x square. And then these were the intermediate missing points that we were supposed to calculate using linear interpolation. And this is what linear interpolation does. So you can see that these green dots are connected to each other in a linear fashion using lines. You can see it clearly here. Let me just zoom into this, and you can see it very clearly here that these points are connected through lines, and that's what is linear interpolation doing here. So this is as far as the linear interpolation was concerned. But as you can very clearly see that this green point should have been on the curve, on the blue plot. And why this is happening is because a line cannot approximate a curve. The line cannot bend. So it is not able to hug the curvature of the original functions. And as a result, this is just going to cause some error because a line cannot approximate a curve. So let's calculate that error. So the actual value of y should have been, let's call it y actual. It should have been minus x intermediate value, the square of it. And the error is y actual minus what we obtained, y intermediate here. This is what we obtained by linear interpolation. So this is what is going to be the error, excuse me. And let's just print this error. So you can see that for every point we are getting an error, rounded error of 0.05. So let me calculate the root mean square error, which should be just the same because these are all, the error is constant for all the data points. Notwithstanding, let me calculate the root mean square error. So that will be, let me call it RMSE, and that will be, so firstly I have to calculate the square of the error, which will be this. Then I have to calculate the sum of this term, which will be this, and then I have to calculate the mean of it. So essentially this is the mean, and then I'm supposed to calculate the square root of this whole expression to calculate the root mean square error, and then I'm going to print it. So here we are. As I mentioned earlier that since the error term is constant, the root mean square error will also be a constant 0.05, and this is happening because a linear interpolation algorithm cannot capture the curvature of a curve, and hence there are going to be interpolation errors. So in this particular case, we have an error of 0.05. So if you want to see the entire plot, here it is. So let me just summarize it again. The blue plot is the minus x square curve, continuous one. We sampled this continuous curve and got these red points. So basically simulating a non-linear discrete data set. And then between each of these two known data points, we wanted to find the missing data, which is basically this green dot. Let me just disable this. So these green ones are the missing data that we are calculating using linear interpolation, the y values of it. So that's how we've got these missing data points. These missing data points should have been coinciding with the original curve, but they are not, because as you can clearly see that they are lines and they cannot bend. So ideally speaking, this green point should have been on the circle, on the curve, like this. Let me just zoom in a bit. So there you are. This is the actual point. This is the theoretical result of interpolation. But because of linear interpolation, this is the green point that we are getting here, which is much lower. In fact, it is lower than this blue point, lesser than this blue point by 0.05. So that's the limitation of linear interpolation if we try to implement it on a nonlinear data set.